and then dive into some projects. As I mentioned, Ted is a colleague of mine here at Old Dominion University, but also a staff scientist at Jefferson Lab. So take it away, Ted.
Thanks, Raul. Can everybody hear me?
Yep, we got you.
I'm just going to share my screen here a second. I think what I'll do is share my desktop so that I can jump around between things. Everybody sees my slides now, science and computation. Okay, good. And my laser pointer. Okay. Okay, so this is a collection of lectures and presentations and things from various sources. So we've done a we've done a physics in Python or a physics and computation thing in the summer in the past, and we decided that it needed to be promoted to a science in Python thing because we're basically covering a lot of stuff outside of just you know, physics, which is our subject, my subject especially, and especially nowadays. Well, much of what we talked about wasn't really specific to physics, so it made sense to talk about science in general. Maybe before we dive in, we should talk a little bit about business. Let me just remind you of the website for what we're doing here. And I guess the presentations will be here at this YouTube link. I'm sure the others will correct me if I've got anything wrong here. And I might remind you also that there are lectures being done in Spanish as well as English. Okay, so why computational science? I think it's not really an overstatement to say that you have to become somewhat skilled, somewhat versed in computational methods if you want to go into any of these kind of topics that are very topical right now. Things like, well, physics and engineering are obvious things that require computation. Now, if you watch the news, you see that there is a heat wave in the Northwest, record-breaking temperatures, 115 degrees in Seattle. And so people are talking a lot about climate, and a lot of climate science is about constructing models and you know, taking some input from physics and meteorology and chemistry and putting them into climate models to try to understand what's going on. So of course, that's a major application of computational science. As a society gets more complicated, we stimulate complicated social systems, and that comes into play if you're talking about things like epidemics. Epidemiology is largely a quantitative social science. Games are something we do for fun, but in a sense, games are just a version of simulations, and we can understand certain things about nature through study of games. If you want to go to Wall Street and get rich, you can get rich by writing models for the economy, well, you can do things like pricing derivatives and so forth. A lot of that uses tools that you develop in computational physics. So as I go throughout here and try to motivate you toward computational science, generally I'll just flash some books and resources that I've enjoyed or I find useful. In terms of climate science, I've got a physics book here that you can look to see what kind of models people use. There's a new one here that is very well written by Lawrence Krauss that is about just the very basics that you need to understand what people are talking about when they talk about things like climate models. So I would suggest reading those. You can find probably your own projects to do in computational Python if you start reading literature like this. Or if you go into climate science, you'll of course be required to do that. Here's a classic book that I like on modeling social systems, complex adaptive systems. And of course, nowadays people talk a lot about epidemiology. And this is a basic introduction to the type of models that you can use to model epidemics or pandemics. This is something that I've actually used to make a project for people, or a little exercise for people we'll talk about coming up, just to get used to doing stuff like this on a computer. And I got the idea to do this for you by reading stuff from even physics literature. So in the American Physical Society, we get newsletters, and there's an interesting article describing some of these classic pandemic models. And they're very emblematic of the way you do basic computational science. So that'll be a useful thing to look at. Here's just looking ahead, giving you a prelude of where we're going to go, an example of the kind of model that we're going to use. So this is what they call the SIR model here. Well, I've given a very surface level diagram of what the SIR model starts out with. You have this idea that there's a population and a group of people who are susceptible to catching some disease. They can get infected, and after a certain amount of time, they recover from the disease. They're recovered and no longer susceptible to the disease. Okay, so we're going to write down a system of equations that tell you about how susceptible, infected, and recovered people may or may not interact as the disease progresses. Okay. The original version of the SIR model is exceedingly simple, and it really only gives a sort of broad picture of what you might expect. Once you have that, though, you can start layering on things like what is the effect of a disease with a long latency period or something like that. Okay, that's getting ahead a little bit. I just want to give you a prelude to where we're going, a preview to where we're going. These are some graphs that I generated from that model, and you see time on the horizontal axis, number of people in a population on the vertical axis. As time goes on, the number of susceptible people drops because people have gotten the disease and recovered from it. The number of affected people grows and reaches some peak and then falls down again. Once everybody has been infected, it's no longer possible to infect more people, so there has to be a peak somewhere. This is assuming that this is a disease that can only infect you once, and once you've had it, you're immune. And then, of course, the recovered people starts out at zero, well, almost zero, if somebody has to start it, but nearly zero at the beginning, and then grows until it is most of the population. Here's a slight generalization of this model. I've allowed a certain fraction of people to die from the disease, so the number of deceased people also grows over time. And actually, maybe I can show you a little bit more. Here is my basic pandemic model. So I'm just showing you this so you can see the sort of thing that I can help you to develop on your own as we go along. We'll come back to this later. So I just run a short pandemic model, and a curve comes up. And what I have down here at the bottom is a slider. Okay. I have a plot that shows me the number of infected people going up, reaching the bump, and then falling down again. The number of deceased people, which I would like to keep low, of course. And just to show you, or just to illustrate what you might want to do with a graph like this, I've drawn a horizontal line to represent, say, hospital capacity. So you have the red line going above that purple line, then the hospitals are in trouble. And then what controls what these graphs look like is an infection rate. How many people if you get the disease, how many people on average do you infect? And I can slide that around by hand and see what happens to the curve representing the number of infected people. So with this computer program, we can put some quantitative flesh on this phrase flattening the curve that everybody started hearing about at the onset of the pandemic. Of course, if we make the infection rate low, for example, by social distancing, we can have a low effective infection rate. We can make that curve very flat, and the bump doesn't rise quite so much above the hospital capacity. Okay. We can almost make it so that it goes below it, and if we increase the infection rate to something huge, we have a big spike. So later in the week, or maybe probably next week, or even further on after that, I'll explain more of the details that went into this. But again, it's just to show you what sorts of things you can do. Okay, another thing that you hear about in the news now a lot is cryptography. And well, probably the most dramatic stuff has to do with people speculating on cryptocurrencies, but cryptography is used in all sorts of places now. You can't really go about your daily life without using it, and it's going to become a more practical skill that people are going to need to develop, is to understand how to do cryptography. So I'll have some examples from the world of cryptography too. I really like this green book here, if anybody wants a really understandable short introduction to the basic concepts behind cryptography. Okay, maybe I should start playing my slides again. And turn my laser pointer on. Okay. One thing that we use computation for a lot that people don't talk about maybe quite so much, but is probably one of the most important things, is just visualization. Okay, and to explain the importance of visualization as a component of doing computational science, let me just reference this article in the Institute of Physics and give you some quotes there. So it's a serious thing, visualizing science and physics in particular. I like to follow the Reddit, the subreddit called Data is Beautiful, to see that put into action. And I'll also give you an example of what I've prepared for some of you to do for these lectures. So if you studied special relativity, okay, if you studied special relativity, you know that weird and maybe non-intuitive things happen when objects start to move very fast, say near the speed of light. For example, they tend to shrink. There's something called Lorentz contraction. If I take a rocket ship and I have it moving at close to the speed of light, it starts to become a very short rocket ship. Okay, that's the Lorentz contraction. You also have things like time dilation. Okay, if you haven't seen that sort of thing, don't worry. Just take it from me that if you took a modern physics class, you'd learn about Einstein and special relativity theory, and those are some of the non-intuitive outcomes that come out of it. And to allow people to visualize it, I've set up an animation that actually shows what happens when I have, say, two billiard balls collide. Okay, so here, if you can see, I've got a dark gray billiard ball coming in from the left that's going to collide with a white billiard ball here on the right. This is going to be what you get in old-fashioned Newtonian mechanics. It looks pretty much like what you would expect. The ball comes in, collides, and goes out. So that looks like what you'd see with billiard balls on a table. Up here, you see something it's the exact analogous situation, but I imagine that these balls are going near the speed of light. Okay, near the speed of light, so they undergo the strange effects of relativity, like Lorentz contraction. So what I have is the white ball sitting here stationary, okay, and the gray ball is coming in from the left, and everything is the same, but I'm going to say that the speed is close to the speed of light. So this ball has been squished into a narrow sort of pancake shape, and it comes in, collides with the other ball, which now takes off, and it also gets its own pancake shape. So they go off to the side as a pancake. Okay. So we can make a whole simulation of these weird effects in special relativity using computational tools. And I use that when I just am trying to explain special relativity to people. Okay. I can show you where I got inspiration from that. There's a game, this is a little bit out of date now, but it's still pretty cool. There's a game engine that allows you to take ordinary mechanics and sort of turn it into special relativity. So everything, like the other things that happen that are weird are clocks start to slow down, things get weird shapes as you try to accelerate this way and that. And here is a YouTube clip describing this applied to something called the slower speed of light game. I don't want to maybe take up too much time just showing the YouTube video. This was created by some people at MIT. And it's based on a child walking around in this game. And the premise is that the speed of light has been lowered. So you start to see special relativity effects just by walking around. And what you see are things sort of bending around, wobbling around. You can get this game. Also, it affects light. So you see light turning all different colors, green, red, so on. You can get this game, just go to the website and play around. So that's an example of basically visualization of a non-trivial set of physics effects. And it's really what inspired me to make this example over here. This is a very, very simple version of what they have. And again, here's kind of what it looks like when you move around near the speed of light. Okay. There are higher level discussions of what computational science actually is. But when you take a class like computational physics, people don't want to say it's just computer programming applied to physics. It's kind of its own separate skill. By the way, maybe I should pause here and wait for questions, if there are any questions.
No questions, we've been fielding them.
Okay, good. Okay, right, so it isn't really right to say that, well, computational physics or computational science is just programming applied to a scientific discipline, but it becomes sort of its own thing. So here's a quote that I took directly from one of my favorite computational physics textbooks. They say computational physics, okay, you can generalize this to say computational science, computational chemistry, computational social science. It basically is all the same thing. Being able to transform a theory into an algorithm, theory or any sort of theoretical framework, requires significant theoretical insight, detailed physical mathematical understanding, and a mastery of the art of programming, and combining those all together. Okay, and I think that's basically a good introduction. But another way to think about computational science as its own separate thing is to start by thinking about the way we catalog different parts of science in the past, say before computers. So some people, especially in physics, but everywhere really, part of science is coming up with theories, models, and hunches. And there's a lot of creativity there, but you tend to work with, say, very idealized scenarios. So in physics, for example, you just talk about a planet with a planet going around a star, a two-body problem, and you don't worry about any complications from real life, even though there's hardly any ever a situation where you only have a planet and a star by themselves, right? You work with mathematics, esoteric mathematics that expresses some deep truth, but then somehow you have to convert that to something that happens in the real world. Okay, on the other side, there's the experimental approach to doing science, empirical approaches, and there you're essentially looking for patterns and trends in the natural world, and there you might have, for example, well, you do experiments, right? And experiments involve being able to change certain things. Well, you're dealing with a messy world, a messy reality, and you want to try as much as you can to fix some things and change other things, and then see what happens. Okay, so for example, if you're growing soybeans or something like this, then you might want to keep the amount of fertilizer on the soybeans, for example, constant, while changing the amount of sunlight that they are exposed to, and see how that affects something. So you introduce these concepts like controls and so forth, and there's a whole methodology surrounding that. So you might want to keep one thing fixed and vary another thing. There are always knobs that you want to turn. You might, in physics, want to vary the, the current through some material while keeping, the temperature constant, or you might want to keep the current constant and vary the temperature, and see how things are correlated with one another. Ultimately, of course, you want to be seeing how these patterns can test the big ideas that you have in theory. Okay, but the methodologies are largely separate. Now, if you are studying some things, you might want to do experiments that you can't do, right? For example, say that you are interested in what happens to a city when it experiences a terrible disease, right? You might want to be testing the way the administration of disease control was set up in that city. So you want to vary that aspect of the city. You also want to maybe vary what kind of diseases get introduced, how bad they are. That's not really an experiment that you can realistically do in real life, right? I mean, you can't really introduce smallpox into a city. You can try to do stuff like that, but you'll probably end up, facing war crimes. So you can do, well, and another example is, in fundamental physics, for example, we want to understand see what are the consequences of some fundamental aspect of our theories. We might want to do something like vary the mass of the electron, right, to see what happens. But of course, we can't do that because nature gives us an electron mass, and that's that. Okay, but in both the example of the city and in the example of the electron, we can create a fake world inside of our computers and essentially do these kind of experiments, right? It's not really an experiment, of course, because it's not reality, but it's a lot more like sort of empiricism than the theory and math, the traditional way of doing theory models and mathematics and so forth. So many people view that as an entirely new third way of doing, of addressing scientific questions. And this is essentially what's meant by that. Another way of seeing this as its own separate subject is as the intersection of all these different sort of sub skills that you need, sophisticated mathematics, insight into scientific principles, right? The ability to analyze data and do statistics. All of these things intersect to give us what we call computational science. Okay, and another way that we can catalog things is by the types of computational science that we do. And these also tend to overlap. I'll try to give an example when I give an overview of the kind of work that I do, of how these sort of subfields of scientific computation overlap. Okay, so you can do numerical calculations, and what that usually means is that you have a very well-defined, say, set of equations, very well-defined discrete set of equations, maybe a set of differential equations usually is what we're talking about. So it's a well-defined mathematical problem. And then the issue is, well, it might be too difficult to solve by hand on a piece of notebook paper, so you write a computer program to solve it. Okay. It's not totally separate to talk about computer simulations, but it's a little bit separate because we usually have a less well-defined, say, set of equations. It'd be sort of like the simulation of the city that I talked about when I was talking about pandemics, you have, you know, many factors that you sort of create a game-like representation of, and usually it'll involve some level of probability, right? So it won't just be solving equations with deterministic solutions. So that would be sort of what you face with like weather forecasting if you're trying to, you know, model the effect of, model how many tornadoes and so on come around. Data collection and analysis is its own separate thing. This is when you get a bunch of data, say poll numbers. If you're polling in the last election and you want to make some conclusion based on the results, then you have huge amounts of data, what people say, where they come from, what their income is, all kinds of stuff like that, and you want to analyze. This is essentially data science, what people call data science nowadays. There's symbolic manipulation. That's solving equations, but not in the numerical sense. So that's more like solving an algebraic equation, solving for x, the sort of thing that you would do on paper. But when it involves too many steps, it's just not really practical for people to do anymore. So if you have say a system of algebraic equations with 300 variables and you know, 300 equations, then in principle you could do that if you had, you know, a lot of time and you know, reams of paper to work on. It would not be very much fun. I wouldn't suggest it, but you could do that. And finally, of course, visualization and animation, which is what I've already discussed, so I won't do that anymore. Maybe to clarify some of the things I've just said, I'll give a few examples. This is essentially from when I would teach a class on computational physics. So numerical calculations are usually what we're talking about is solving some set of differential equations. Okay, so probably the most famous differential equation that you would encounter in intro physics would just be Newton's law of F equals ma. By the way, if you haven't seen differential equations or physics, don't worry, you won't miss out too much if you don't follow what I say on the next few slides. It's just one example of many that we can give. I'll try to explain more as we go on. We'll talk about derivatives and differential equations as the weeks go by. But it's a differential equation because A, the acceleration, is a second derivative of position with respect to time. Okay, so it's an equation involving a second derivative. So the second order differential equation, and F is usually we'll put something in for F, for example, Newton's law of gravitation. Okay, and then it's a matter of figuring out what the solution is. What happens to X as a function of time as a result of that equation? Okay, so here's just another way of writing what I just said. A is the second derivative of position with respect to time. Okay, and we put something in for F. We have to solve this equation to say, what is X as a function of time now? That's the problem. And if we took, for example, for F to be the gravitational law between two gravitating bodies, the other equation that you probably see in the first semester of physics, say in high school or an undergraduate, okay, we can solve that. Okay, we already know what the answer is. We don't need a computer to do that. Right? If you study this problem, you know that the answer is that you get a path that is elliptical. Okay, but you might want to say, what if I want to solve this equation, but I want to make this force law that I wrote down here a little bit more complicated than what I have. So I add some extra terms. Then it might not, either I can't solve it because it's impossible, or else it may be just too complicated and I don't want to solve it. Then I can use an equation, and I can use visualization, and I can get, for example, I can see, for example, that the extra terms that I add in that equation will make it not an ellipse, but an ellipse that precesses. So this is an example of another one of the exercises that I gave for solving differential equations. Okay, and then if you go on in gravitation, instead of having Newton's differential equation, you have Einstein's differential equations, which are 10 partial differential equations, which are horribly complicated. Okay, but you need to solve them. For example, here's what they look like symbolically, and you're not supposed to understand what that means if you haven't studied relativity. It's just to show you, give you a heads up on what's coming when you do gravity. It's a compact way to write a whole bunch of differential equations that have to be solved simultaneously. And you can use extensions of the kind of techniques that we're going to talk about to do things like solve those equations and figure out how gravitational waves propagate out. And gravitational waves are a big hot topic right now because they were only first seen about 5 or 6 years ago. Okay, and people spend decades. Let me just open up visualization of the simulation, supercomputer simulation. Okay, this is essentially solving differential equations with, well, not with Python, but computationally. I don't think they use Python for this. But it's what it's showing is the density of, or the strength of gravitational fields as a function of time when you've got two black holes that are spiraling around and collapsing into each other. Okay, don't want to take too much time on this, so maybe fast forward a little bit. Here's another version of that. Simulation of gravity waves emitted during a merger. Okay, so this is all just stuff for you guys to play with. You can come and look at this after I'm done today, just to get motivated. Okay, these gravitational waves now are getting detected. Okay, it's a massive undertaking to detect them. These are the detectors, and we need at least 2 of them. Okay, this one is in Washington State. This one is in Louisiana, over here. Oh, I'm not using my laser pointer. Okay, I think you're going to have some lectures in the other meetings about gravitational waves, so I don't think I'll spend too much time on that. Okay, other things that you can simulate are, well, weather forecasts, social systems, complex dynamical systems, and what makes them, again, I'm sort of repeating, but it's important. What makes this class of simulations different from the direct numerical simulation is that they involve stochastics, or elements of chance. These are stochastic models, okay? That can be fun because, well, one thing you have to do is generate lots of arbitrariness in your computer simulations. So one thing you have to think about is, how do you generate arbitrariness computationally? And we'll do some of that coming up. Here's just another list of all the things that people simulate using, say, stochastic type of simulations. Okay. And eventually you have to deal with nonlinear things. So that's finally another thing that we'll talk about. So I think what I'll do now is discuss my own research a little bit. That'll provide some context to where I'm coming from with these things. So I'm going to leave computation for a bit and try to give the fastest overview of my own research that I can. Okay. So when I talk about what I study is quantum chromodynamics. Okay. And let me just give you a brief description of what that actually is, what I'm talking about when I say quantum chromodynamics. So it's one of the fundamental interactions. What I mean by fundamental interactions, well, you might know, you might not know that there are 4 fundamental interactions. By fundamental, I mean the interactions that are the source of all other types of interactions. So every interaction in nature can be boiled down to either one or some combination of these types of interactions. Electromagnetic interactions, okay, and also if you go into quantum mechanics, quantum field theory specifically, you realize that every interaction is mediated by its own particle, interaction particle. So electromagnetism, that's, well, you see electromagnetism all around you all the time, but in particular, it's responsible for binding things inside atoms and molecules, so like electrons bound to, nuclei to form atoms. And it gets mediated by a particle called the photon. So light is electromagnetic waves. So light, you can think of as streams of photons. Gravitation, well, everybody knows what gravitation is. It's what makes you fall when you jump off a building. And well, it's presumably it gets mediated by something called a graviton. The weak nuclear interaction is probably the most difficult to explain to non-particle physicists because you don't really encounter it much directly in everyday life. The best way to think of it is it's what's responsible for most of nuclear decay. So like the fact that a neutron decays into a proton, okay, that's due to the weak interaction. But what I study is the strong interaction. Okay, that's what is responsible for, say, binding nucleons, protons, and neutrons inside of a nuclei, a nucleus to form a nuclei. And it's really, really strong, as its name suggests. And so it can store huge amounts of energy. Okay, so the strong nuclear interaction is really why there's so much energy involved in nuclear physics, right? So when you have nuclear reactions and stars and all that stuff that involves huge amounts of energy and uses of E equals mc squared, that's due to the strong interaction. Okay, and what mediates the strong interaction ultimately is gluons. Now, the strong interaction is a little bit hard to think about because the interaction between the neutrons and the protons, for example, is not the fundamental interaction. Okay, you have to go down, dig down a little bit further. So just as there are just as there are fundamental interactions, there are also fundamental constituents of matter. So let's go through that as well. And I always like to use a picture of my mom's dog, Opie, as a starting point to give you a sense of scales. His nose is about a centimeter. Unfortunately, Opie died recently, but he's still here. And if we dig down into his nose to about 10 to the minus eighth of a centimeter, so 10 to the minus eighth, that's a really small, right? It's not quite a billionth of a centimeter, right? Then we start to see atoms. So this would be, I guess, a helium atom somehow ended up in his nose. And it's the electromagnetic force that binds these electrons that are zipping around out here in these rings to a positively charged nucleus here. Okay, you can sort of think about those electrons as exchanging photons with that nucleus to keep them bound together. But then if I dig in a lot smaller, about a factor of 10,000 or so, into the center of that nucleus, I can see that it's made out of nucleons. And you might think that, well, since the photons are being exchanged between the electron and the nucleus here to bind the constituents of the atom, there must be a fundamental particle, a fundamental force particle being exchanged between the proton and the neutron here, binding, say, the protons and neutrons together to form a nucleus. There's a particle exchange called a pion, but the problem is that that isn't really, wait a second, what's going on? I have lost control. my slides here. Just give me a second, I'm having some technical difficulties. Okay, there we go. So if we zoom down even further and look inside of, say, the proton, you'll see that it's actually made of its own subparticles, its own constituents. Okay, I've drawn 3 of them here, and they come in colors. I've got a red one, a blue one, and a green one. Okay, and these are called the quarks. And these are the things that actually bind together in the most fundamental way. So they're exchanging particles that we call the gluons. Here are the gluons. These springy things here are meant to represent the gluons. So they're bound really, really tight, and they're bound so tight that the quarks can never actually be separated by more than about a femtometer, by more than about 10 to the minus 13 centimeters. They're stuck that close together. You never actually see a quark by itself. You have to do some experiment that penetrates really deep inside of the proton to see evidence of an actual quark. Okay, and what's fundamental is the interaction between the quarks that causes them to bind together to form a proton, similar for the neutron. Okay, and then there's a residual strong interaction that's left over between the proton and the neutron that forms the binding in the nucleus. It's sort of analogous to how there's a residual electromagnetic force left over between atoms that cause them to bind and form molecules, right? The most fundamental interaction is the interaction between the electrons and the nuclei, but there's a leftover amount of electromagnetic interaction that also allows atoms to bind into molecules. Okay, if you want to see another description of this, I've got a YouTube link down here that you can go to that is really very good. Okay, so what kind of experiments do we do? Here's a cartoon of the experiment. This will lead up to what we have to do with computers. Well, in order to see that something like the proton is made out of quarks, we have to hit it really hard with something that is close to being point-like, so that it can be, you can think of it as like a surgical probe of what's inside of the proton. So we send an electron flying in from the left at as high energy as we possibly can. And here's a proton coming in from the right. Actually, as a side note, remember when I used relativity as a visualization example at the beginning, and I discussed how when something round is moving, it gets squished into a pancake or oval. This is just another version of that. That's why I've drawn it this way. Not really relevant to what we're saying here, but interesting nonetheless. So they come in, and then the electron hits the, say, one of the quarks. That's what this picture here is supposed to indicate. And then sends it flying out the opposite direction from the other quarks. That's what this picture right here is supposed to indicate. And the electron comes flying out. And the idea is that by looking at what momentum of a scattered electron is, and by looking at whatever is going out the other way is, I can work backwards and infer that there must have been some sort of quark-like structure inside of this proton to begin with. This is a kind of experiment that we do at Jefferson Lab, by the way. This is exactly how it works, right? They even look like they're yellow with green, blue, and red particles in them. Okay. Well, it's not quite this way. If it were this way, it would be easy to write computer programs to tell us what exactly we should see in collisions like this, right? Especially if it's just a matter of, say, billiard ball type collisions. But we know, I already said that quarks never actually can end up alone, right? You never see a quark entering an experiment. You've never encountered a quark directly in your daily life. So what happens on the previous slide, what must happen, we have to say what must happen, is that when the quark is flying out and the other quarks are flying out, some complicated interaction between these outgoing quarks has to take place to cause them to turn back into the kind of particles that we do see, like protons and neutrons. Okay. And so I can layer one extra layer of complexity on top of that cartoon that I drew before. I can say, well, actually what happens at the end is that as these quarks come out, something interesting that I don't quite understand yet, so I'm going to draw it as a bunch of clouds, takes place and ensures that whatever happens with these quarks, in the end, what you see are particles like protons and neutrons. That's what this green and lavender blob are supposed to represent. So something happens here. And I can try to write a computer program that takes into account at least some of the physics that I think goes on in there. Okay, so what we're doing is building up a simulation, essentially. Okay, and then I can keep adding layers of complexity on top of that. What if, say, two of the quarks collide before all the cloud stuff happens? I can try to build that into my simulation. Or what if one of the quark actually splits into, this can happen, splits into two other particles that then undergo all the cloud stuff? Okay, so things start to get more complicated than what I can handle when I'm writing on a piece of paper. Okay, more specifically, let's keep talking about the stuff with quarks for a little bit. Imagine that I've got a proton coming in again. One thing I can do, well, you might be able to figure out that the interactions, you might be able to guess that the interactions between these quarks that lead them to form a proton are incredibly complicated. And it's really impossible to just take out a piece of notebook paper and figure out how that happens. I'm talking to, say, Dr. Briseno about that because he tries to deal with that head on. If we're talking about a collision, what you might want to do is say, well, maybe for what I want, all I need to know is how much of the total momentum of this proton, the total energy and momentum of this proton, is carried on average by one of the quarks. If I know that, then I can possibly do a bunch of subsequent calculations just with that bit of information. Okay, so we call that x. X is the fraction of the momentum carried. Okay, so in order to do that, to allow some of the complicated calculations like what you see at the Large Hadron Collider, if you've heard of that, if you've heard of the Higgs boson and so on, so people just measure that. The fraction of momentum typically carried by one quark. Okay, and for about 30 years, there have been groups that have been trying to compete with one another to nail down what that distribution is. Here's a link to just one of those groups. This is the fraction of different types of quarks. There are different versions of quarks. They all come with their own names, up, down, and so on. That's kind of a side issue. But say red here is the red quark. What this graph is saying is that there's this fraction of the proton momentum typically carried by that red quark. Okay, as you might imagine, we're extracting that information from this complicated process like this. So it involves a lot of intermediate computation, and it involves data. So we have to combine computation with data analysis to ultimately get to a graph like this. So this is an example of that overlap of different things that I discussed at the beginning, way back here. Okay. So we have data. Of course, we have computers, and we have the theory here in blue, all overlapping now. Okay, and here's just an example of the data analysis that leads to those kind of graphs. This is a graph of basically the probability for that kind of collision that I just described. There's just more examples that you can look at in your free time. Okay, so that's an example of basically all three of these things applied at the same time, but also there's visualization and animation. Now there's an example of symbolic manipulation that comes up in my work. okay? So I drew this picture where I talked about what happens when the electron collides with one of the quarks, okay? Say that we know the distribution of quarks inside of a proton, like this picture already. Now if we know that, presumably we can figure out what happens when the quark hits the electron or hits something else in general. It doesn't have to be the electron. Okay, and we have a whole set of tools that were developed over the last century for doing that kind of calculation, and they're represented here in this figure up here at the top. This is called a Feynman diagram. You may or may not have heard of Feynman diagrams. And what they essentially are is a way of translating complicated mathematical expressions into pictorial diagrams that we can think about and that help us to analyze, that help us get our minds around these actual calculations. Okay, so these are supposed to be sort of cartoon representations of what is happening, but really they are representing, each one represents a specific large mathematical computation. Okay, and we start by writing, we draw this diagram, we translate it essentially into a bunch of integrals, and then the task is to actually calculate those integrals. And some of them we can actually do on a piece of notebook paper. We don't want a computer to do it because we want, these are things that we can calculate. We know that like a big algebraic equation with 300 variables, a large linear set of linear equations with 300 variables, we can calculate it. We just don't want to spend that much time. This is what a typical diagram like this, what the expression looks like. If you were to sit down with your pen and paper, you could in principle get this. Actually, people have done that kind of thing. And actually, you'll note that it ends in a comma. That's because I couldn't fit it on the slide. It goes on, if I were to, I would need several other slides to fit the entire expression. Really, it's just a normal, it's an ordinary mathematical expression. You see a bunch of polynomials. This is that x, that momentum fraction that I was talking about. You see a bunch of logarithms. See a dilogarithm, which you may or may not have seen before, but it's just another function like a logarithm. You see a bunch of just numbers like 43 over 108, blah, blah, blah. So it's just a thing that you could calculate, but nobody calculates something like this just by pen and paper. Well, maybe some crazy people do, but no normal people do. Instead, what we do is we have a computer program that does it for us. And actually, I calculated this using a computer program. Okay. So that's just to add an example of this last bullet down here. And also, I would note in passing that that feeds into this overlap of different methods because we ultimately have to use this to get that distribution of quark momentum fractions. All of these things mesh together in our work. Okay, and finally, there's the kind of simulation technique that I talked about at the beginning that involves stochastic methods, elements of randomness to model extremely complicated stuff. We call those Monte Carlo event generators in particle physics. And I'll give you just a link to read more. The picture here is to represent the complicated interaction that is being modeled. So what we have, if you see these big green blobs here, they are like protons coming in. So it's just like the picture I drew before with the yellow protons squished to a pancake. They're coming in from the right and left, but there are tons of gluons and stuff that are getting radiated as they come into this complicated process. And they all interact in some complicated way. They fuse and then they split to other things that then split to other things that split to other things. So this is, again, not something that you would calculate by hand or even analytically. You would basically model it with an element of randomness, the same way you would model, say, a weather forecast. And this is just to show you the sort of plots that you can then compare with data. And finally, there's an element of visualization here because you can show what an event like that actually looks like inside a collision inside of a particle detector. These lines show the, the tracks of particles, and then where various parts of a detector get signaled, and so forth. Okay, I think now is another time to pause, so if there's anything that needs to be addressed.
No, we're still fielding them. All good.
Okay, good. So let's get into the tools. So a lot of these kind of calculations, this is something that we're not going to use, but I want to mention it as an introductory thing in passing. Once you start doing really serious calculations, you tend to need a lot of computing power, especially for simulations. I just want to mention that nowadays you can basically get, you can get support from anywhere. Here's some links. So even say Google and Amazon can provide you with supercomputing resources. You need to choose an operating system. I'm using Mac right now. Linux and Unix are good. Windows is okay, I guess. Just give me a second here. I am again having trouble. For some reason, this keeps causing my computer to freeze. Okay, languages and compilers. So this is a slide that I normally use in a class on this. So we're going to be using Python. So it maybe isn't entirely relevant, but it's still useful to think about languages. So you need to choose a language. And I think that normally if you want to do a lot of good computation, you need to know several languages. And basically just by experience, you'll figure out which ones are good. And then just have a good book. But nowadays I want to emphasize that you can pretty much learn anything about computer programming and computational science from the internet, from Google. Okay, there are thousands of really slickly produced, really good resources that will teach you pretty much anything you want to know. Videos, blogs, things like that. If you don't know something and you just, or if you don't know something, just type, I don't know, blah, 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 what you don't know, you'll probably get an answer immediately. I'll give you some examples there. Languages that have lots of existing libraries are really good if you want to do computational science, because you generally don't want to spend all of your time reinventing the wheel. There's something called problem-solving environments. These are essentially very high-level computer programming systems. There are things like Mathematica, if you ever use that, which so you generally don't have much control over anything. It's basically everything is done for you. But they tend to be things you have to pay for, so that's a downside. But they're also very useful. So I just want to mention that in passing. They can be very useful for what we call prototyping. So if you have some idea of a program you want to write, you can try it in something like Mathematica first. So they're good for small and medium projects, good for prototyping. But for something where you want to have a lot of control, you would use something like a compiled language like C++. Okay, so this is all just a little bit of my advice that I normally give. I'll try not to spend too much time on it. I think for doing computational science, you need to strike a balance between thinking about the computational resources too much like black boxes. You don't want to be reinventing things all the time, but you want to understand what's going on under the hood, at least to some extent. For decades, people have been writing computer code that does all kinds of basic things, and it's kind of silly to be reproducing that all the time. On the other hand, if you want to do something new and innovative and novel, you often have to understand what's going on. So it's good to try things a few times on your own. You need to ask, how much do you really need to customize when you're deciding how much you want to incorporate with modules and so on, and how much you want to rely on existing resources. Nice thing about Python is that it's got tons of libraries and repositories of existing software. So be aware of that and know to look for that. Okay, so project design. I'm going to spend a little bit of time just telling you how I think scientific computing projects should be organized. This is the sort of thing that I would tell students in my class that they need to do, when they're doing projects that I assign to them. And it's easy to sort of gloss over these things and roll your eyes at them, but it's also very important, I think, in the long term to develop good habits. Okay, so the first thing I think you should do is write down what you're going to do on a piece of paper. Okay, like old-fashioned thing with a pencil and stuff like that. Write down, the ideas that you have clearly, if you're doing it with your friends, do it on a whiteboard. Explicitly write down which equations exactly that you need to solve. Okay. And this is the most important thing. Draw lots of diagrams and pictures, and write a code that is not necessarily correct code, but just a sequence of instructions in the order and organization that you want them to be in. And don't worry about syntax or anything like that. Just write it on a chalkboard or on a whiteboard or something like that, and in a pictorial form. Make sure that when you start writing your code, you include comments everywhere. I'll come back to this in a section in a bit, and make sure that it has a logical structure to it. And once you've finished with a setup of your project or your code, you need to validate on simple cases. Okay, what I mean by that is, say that, just to keep things simple, you write a computer code that's supposed to add numbers together. Make sure that you try it with, say, 1 + 1. Okay, and see that it gives back 2. Okay, or if you do something more complicated, say that you want to write a computer program that describes the trajectory of a rocket. Okay, try what happens if you want to look at the trajectory as a function of how much fuel you put in the rocket, for example. Make sure that you see what happens when you put no fuel in the rocket. Okay, if it reaches the moon, then it means that there's something wrong with your computer code, right? Or if you want to make a hot air balloon as a function of the element that you put in as a gas, see what happens when you put in lead. Okay, that's what I mean by validate. Okay, that's another thing that people tend to just skip, and it's really important and simple thing to do, and can save weeks. So I'm going to go through a few examples of the diagram type of technique. I'm going to belabor this a little bit just to get it out of the way. Here is probably one of the simplest flow diagrams that you'll ever see. Is, well, I could start by saying, well, I want to model infectious diseases. Well, step one, we go up on the whiteboard and think, well, maybe the best thing to do is, the simplest thing to do in the absence of anything more sophisticated, is to just take all the people in the population and divide them into 3 categories. People who are susceptible to the disease, they can get it. People who have recovered, they no longer can get it. And people who are infected, they have it. Okay, that's the simplest thing. It's always best to start with the absolute simplest thing. So you go up on the whiteboard and draw a picture like this. And then that's your starting point for developing a better model. Or if you do projectile motion, this will be one of the other projects that I will suggest to people. This is an example. I believe this is an example of the Paris gun from World War I, which was shelling Paris from 70 miles away. Okay, one of the biggest pieces of artillery in history. So the physics problem, you say, well, what do we need to, or the science problem, I guess I should say for this lecture, what do we need to write down as our set of scientific or physical theoretical principles? Well, we've got the basic elements of projectile motion. So we've got to draw an axis. That's a good thing to have if we want to describe what's going. So we might just draw an axis on the board. We know that we need to draw an origin, the simplest things you need to do right away. And we know that whatever this projectile is, it comes out with some velocity. And if you've taken intro physics, again, don't worry about the details here. If you haven't taken intro physics, just follow the spirit of my methodology here. We know that basically this, if we strip away all the complicating factors like air resistance, the Coriolis force, everything like that, then we have a constant acceleration caused by gravity, and this projectile is going to follow some sort of arc. In fact, we know how to solve this with paper and pencil. Okay, but we might want to make it into a code so that we can start layering on extra complications later, like air resistance and things like that. Okay, so how might we draw a diagram for this? The simplest thing, first thing we have to do is we have to say, what is the initial V0? What is the acceleration due to gravity? What is the angle that a projectile is coming out at? Okay, so I'm going to say initialize constants. That would be step one. Okay, I'm being very coarse-grained here, very crude. The next thing would be to say, do a bunch of basic calculations. Okay, that would be using the formulas from your intro physics textbook, which we'll do a little bit later. Okay, now I say loop over time. Computers are really good at tasks that involve taking some simple process and doing it a gazillion times really fast. So this is a strategy, how we try to convert complicated problems into something that computers can do. We say take a complicated problem like this, and well, it's not that complicated, but take some complicated problem and see if we can break it down into little bits that are individually not all that complicated. Okay, if we can break it down, and if it's instead of being one big complicated problem, if we can have it be a bunch of little simple problems, then that's ideal for a computer. So for example, we can say what happens a tiny fraction of a second after this cannon is fired. The projectile has gone some distance. And if it hasn't gone very far, then we can calculate that pretty easily using our intro physics textbook. And then we find a new position. And then we can let it go for a little longer and find a new position, and a little longer and find a new position. And we can find what its position is at different increments in time. That's nice because at the end of the day, we can plot all of that and see what the trajectory is. But that means that we're basically doing something over and over again. So that's what I mean by loop over time. And if we were going to expand this out into a more detailed diagram, which you should do eventually, then you would write the details of what happens at each step in time. And then finally, you would gather all of your results and output it somewhere and then make a plot or answer whatever questions you have. Okay, now once you do a very simple diagram like this, you need to fill in the details and flesh it out. So it's always good to, you really can't start simple enough. Make it so simple that you feel silly doing it. And then start fleshing things out. So in this first initialization step, we now maybe will start again, but specify what the initial things that we want to input are. So G is the acceleration of gravity. V0 will be the initial speed. theta will be the angle of launch. And we're going to want to follow the trajectory for some period of time. Let's call that period of time capital T. Okay, now let's flesh out what we mean by this loop over time. So loop over time, remember, we're going to say we look at where the projectile is after some small step in time, do some update, look at it where it is, look at where it is a small step after that, do some update. So you'll see as I fill this in, but these blue lines are representing the loop aspect. As I go into the loop, the first thing I want to ask at any stage in the loop is whether the time, if I want to continue doing this loop, is the time that I'm looking at somewhere between 0, which I'll say is the starting point for this sequence of events, for this when the thing is fired, and capital T, which is the last time that I'm interested. This is the total time that I'm looking at, because I only want to keep doing this loop if T is in that range. Okay, so I have to write a program that checks whether this is true. If it says yes, this is true, then it will use some set of equations, which I haven't written down yet, to calculate what the position in the x direction is, in the horizontal direction, and what is the position in the vertical direction, the y direction. Okay, store them and output them somewhere. And then it goes to this blue line, which takes us all the way back up to the top and repeats everything again. Okay, I'm still skipping some things because I'm showing you how we're going to sort of flesh this out gradually. I'm going to hit the big points and then keep filling it in until we get something that we can write in a computer program. Okay, well, here I said what happens when yes, what happens when no. Okay, then we have to ask, why isn't T inside of this interval? Well, if it's less than 0, say if it's negative, then that means that we're at a position in time that's before the launch actually took place. So we might want to just go back straight to the loop and go back to the beginning and not do anything but just maybe move time up a little bit farther before we continue. And if that's not the case, then that means that time is greater than capital T. So it's already reached the last point that we're interested in looking at. So we go down here, and if that's the case, we want to say, let's output whatever we have and say that the program is done. So this is just an example of how I've taken this extremely crude flowchart and fleshed it out a little bit more. And then you would want to start to flesh it out even more than this before you actually start typing in your Python code. Okay, these are the sort of habits that are really good to develop. Some more habits. Your code should be as clear and simple as possible. Okay. Keep the different bits of logic inside of the code separate and identifiable. That's called structured programming. So when you look at your computer code, you should be able to map each little block to something in one of these kind of diagrams. And include tons of documentation, include tons of comments inside of the code. So it should be, there should be almost more commenting than there are codes. Okay. If you're someone who's mathematically oriented, very mathematically oriented, and you like tricky computer programming stuff, it's tempting to try to come up with, nifty little tricky techniques to try to maybe speed things up. This is not something that I would recommend to students when I teach computational physics. Nowadays, you have computers that can do pretty much most of what you actually want to do without having to use tricky techniques. And the tricky techniques tend to just make reading the code much more difficult than it needs to be. So just do it as direct as possible, but as simple as possible. And finally, don't use stuff that depends, at least to the degree possible, don't use stuff that depends on exactly what type of computer a person is using. Okay, more on comments. Each computer program should start with a block at the very beginning, like a giant paragraph telling exactly what everything does. It should list what the say the variables are and what each of them stands for. And then again, with each subsection, there should be, say, a paragraph explaining, say, what each function does and so on. You're going to have to give identifiers, so basically names for variables. And one thing that students have a tendency to do, actually not just students, but everybody has a tendency to do, is to give names for things that don't have any obvious meaning, right? So if you have a variable, don't use x as a variable. Okay, for momentum fraction of quarks that I discussed before, use x as a variable. But for example, back here, I had the acceleration of gravity was g because g stands for gravity. So that's a pretty good identifier. You might even just write out the word gravity, though, inside of your computer program. A bad name for a variable like that would be variable number 1 or something like that, because nobody's going to know what you're talking about. I've had other students who will do things like the first variable they encounter, they name x. The next variable they encounter, they name xx. The next variable after that is xxx, okay? Now, when you're doing that, you think, well, it's obvious what I'm doing here. It's just a name, so why make a big deal about the name? But then you wait just 2 weeks or so and look at the code, and it will be something that you just basically have to throw out and start over. Okay, I don't mean to belabor that. And labels for all output data, same thing, meaningful identifiers for variables, meaningful identifiers for anything that you're going to output, and you should output everything. Okay, Python. Finally, I'm talking about Python. Sorry, I spent most of today sort of rambling, but Python is, there are many reasons why you could use Python. The exact programming language is not super important in my opinion, but Python is a very user-friendly language. It's got all the nice features of object-oriented programming, which if you don't know what that is, we'll maybe get into that later, but it's a way of organizing computer program logic. So the most famous example is probably C++. So Python is like that, but much simpler in terms of writing code than, say, C++. So you get a lot of the nice features of object-oriented programming, but without some of the nasty, annoying things. There are lots of existing libraries and existing codes that have been written that you can use and find for free and easily by just using Google. And it's a very popular programming language now. You can find tons of resources that are much better than me online. Here's a link to some tutorials that you can find that are very well organized. Well, let's maybe do some examples now. Let's see, how much time do we have? We have a lot of time. We go till 5, right? Okay. That's a bit long for me, but I'm going to get hoarse. So, okay. I stripped it down to a basic set of topics to cover. Again, I think probably the best thing for anybody is to go through tutorials and get their own books, but I'll try to give the best sort of quick overview, a basic introduction of using Python that I can think of. Operations is the thing we'll start with. So actually, maybe I'll start doing stuff myself here. And we can go through it. So operations are mathematical operations, or what I have in mind. Things like plus, minus, star is multiplication, divide is division, of course. Star star means raising something to a power. And the percent sign is a nice, interesting operation. It's modulus, so it's basically the remainder when you divide two numbers. Okay, so for example, 5% 5 would be 0 because there's 0 remainder. Okay. Let's maybe just play around with that. So I'm going to do, can everybody see what I'm typing here? I'm doing it now in my terminal. I'll give an example in Jupyter in just a second. Say Python. Okay, I can do 1 plus 1. That's the plus operation. Pretty simple. That's just 2. Okay. What else? What is 3 star star 2? Maybe pause for a second and see if you can figure out what that is. What is star star? That's raising to a power. So that's 3 squared, right? So that's 9. Okay. Mod, mod is a very nice operation that I'd like to work with. 5 mod 5, that's what I've written down here. 0, why is that? Because when you do 5 divided by 5, there's no remainder. Okay, so what is 5 mod 6? Maybe think about that for a second. What do you think it's going to be? Give you a few seconds to work it out. 5, does that make sense? 6 doesn't go into 5 at all, right? So 5 divided by 6 has 5 as a remainder. How about 7 mod 6? So 7 divided by 6, 6 goes into 7 one time with 1 as a remainder. Okay, or 8 mod 6, 0. Okay, so those are operations. These are arithmetic operations. Now there are assignment operations. Okay, that means that I'm setting something equal to something else, or I'm making something related to something else. Okay, the most basic one, of course, is equals. So if I do, for example, x equals 2, that means I made x equal to 2. So now if I type x, that's 2. Okay, how about x plus equal? Does anybody have any idea? X. So now x is equal to 2. What if I do x plus equal to 1? Maybe see if you can anticipate what that's going to be. Okay. It's equal to 3. Do you understand why that is? So what it does is it takes what x already was and adds 1 to it. So now x is equal to 3. What if I do x plus equal to 5? Can you anticipate what that's going to be? Why is it 8? Because x was equal to 3 before, and then plus equals means that I take what x was and I add what's on the right, so I add 5 and I get 8. Okay, and the same for the other operations that we have here. How about comparison operations? Okay, I have an operation that's equal here. What does that do? So say x, let's do, well, first of all, note that x is still equal to 8 from last time I messed around with it. Now if I do x equal to 5, that does something curious. It returns false. So what the comparison is doing is it's checking whether the comparison equal sign is doing is it's checking whether x is equal to 5, which returns true if it is, and returns false otherwise. So if I did x equal 8, I would get true because x was equal to 8. So it's not changing the value of x, it's just checking whether some aspect of x is satisfied. And I bring this up because it's one of the areas that leads to typos a lot and mistakes. I've had people spend like 2 weeks trying to debug a code when it turned out that, say, they had switched equals with equals equals. Okay, so you need to keep those concepts separate. Then there are other comparison operations like exclamation point equals. That's basically the opposite of equals equals. It returns true if the things are not equal to each other, and it returns false if they are equal to each other. So for example, here, x is still equal to 8, but if I do x not equal to 8, that's false because x is equal to 8. But if I do x not equal to 5, that's true because it's true that x is not equal to 5. Okay, is that clear? The others, I think, should be relatively self-explanatory. The greater than or less than signs. The only thing is that they're greater than or equal to signs, like this one, or less than or equal to signs, like this one. So for example, what is x now? It's still 8, right? So x greater than 8, that's equal to false because x is not greater than 8. It is equal to 8. But what if I do, here's x greater than or equal, x greater than or equal to 8. That's true because x is greater than or equal to 8 because it's equal to 8. Okay, so the other point here is control structures. So again, I've drawn here the type of figure that you will see in your flowchart diagrams that I was urging you to write before. A control structure is basically something that checks whether something is true and then does something else based on whether it's true or not. Okay, so you go along in the code. If is probably the simplest one that you can imagine. So you say, if something is true, remember we just did comparison operators, so that's the way that you figure out if something is true or false. Then you do something. This diagram is showing that. So starting here in the code, the diamond is the if thing. The diamond is where you say, is something true? If it turns out to be true, you go into this block and do whatever is written in this block. And then you go and you finish the code. Okay, if it's not true, you just go and finish the code without doing that thing. Okay, so an example is here. Say that I start with x equal to 0, or excuse me, x equal to 2. Then I check if x is greater than 0, print, uh-oh. Okay. And since 2 is greater than 0, it prints uh-oh. Okay, so let's maybe see how that works, and we can pick apart some of the details here. So I'm going to do x equal to 2, if x greater than 0. So the one thing, there's several things here to be careful about. There is this colon here at the end of this if statement. So if x is greater than 0. And the other thing to be very careful about is that you need a tab. Note that the print has been tabbed in. So this is how Python separates different parts of code. So many other computer programming languages, you'd have like braces or brackets saying the end of it, or the beginning and the end of like an if statement, or the beginning or an end of a function or something like that. So Python, instead of doing that, uses spacing. So we have to tab in like this. You see, I'm going to blow up a little more. So I said print. Uh-oh. This. And it says uh-oh. Okay, so that's a simple example. One generalization of that is you can say if it satisfies one condition, do something. But then if if it satisfies a different condition, do something else. So that's the if and elif combination here. And I think the diagram says it all. Going along the code, I say if something is true, then do this thing. If it turns out to be false, do this other thing, and then end the code. So for example, here's another example. Start out with x equal to -1. Okay, if x is greater than 0, print uh-oh. It's not greater than 0 because it's negative. So it goes on to this elif statement. Elif, if x is equal to -1, print hooray. It is equal to -1 because I said it like that there. And it prints hooray. Okay. Okay, the while structure is what we call a repetition structure. So it basically says, check if something is true and keep doing it as long as it's true. So again, the diagram would be something like this. I'm going along in my computer code, and then I say, well, is something true? If it's true, I do this thing. And then I go back and I ask, is it still true? And if it's still true, I keep doing that thing. Then I go back and I say, is it still true? And then blah, blah, blah. I keep doing that until it's no longer true. Then it's false and I end the code. So here's an example. I start with something. I say I is equal to 0. Then I say while I is less than or equal to 10, okay, print I, and add 1 to I. So I start with I equal to 0, and I'm going through, it says while I is less than or equal to true. It sees, yes, 0 is less than or equal to 10. So it prints 0, and then it adds 1, and then it repeats again. Now I is equal to 1, so is I less than or equal to 10? Yes, it still is. So it prints 1, and then adds 1. Now I is equal to 2. It goes back. Is 2 less than or equal to 10? Yes, so it prints 2, and so forth, until it gets to 10, prints 10, then add 1. Now it's 11, says, is 11 less than or equal to 10? No, so it stops. So this is one of those loops. This is the kind of thing computers love to do, just check something over and over again and continue to do some process over and over again. For is kind of similar. You can do a lot of the stuff with for that you do with while. Here is a very typical type of loop type thing that you'll encounter. This is an example of how for works. Say that for I in range is another utility that you'll use. Range says is I such that it is 1 up to something less than 10. Okay, so what this code is asking is I inside the range 10? And if so, it prints I. And then it automatically iterates, meaning that it adds 1. Okay. So it says, is I, first it says in range, so it does I in range means I is 1, prints I, then it adds 1, I is in range, so it prints 2, then adds 1, prints 3, and so forth. Here are the basic elements. Note that it doesn't print 10. So 10 is not included, the last digit is not included in that range. Okay, maybe we should do an example. One, two, three, four. I wanted to go all the way to 5. I would make that a 6. Okay, the last thing maybe that I'll probably talk about today are lists. Lists are going to be something that are incredibly important to work with. Well, it's what it sounds like. It's a list of things. The simplest case is a list of numbers. And here's an example. Nums, I've defined here to be a list. And it's a list that includes 1, 5, 3, and 2. And then the way you access a particular element of the list is with brackets at the end, and then a number indicating the position inside of the list. Now, note that the list starts with the label 0. So nums of 0 is this element of the list right here. So it starts with 1. Nums of 1 is actually the second element of the list because it comes after 0. So it's 5. Okay, is that clear to everybody? Nums of 3 is actually the fourth element of the list. Okay. You can do the same thing with letters or other kinds of, like characters. You can say make a list of characters. Okay, we can do that. Let's do that explicitly. Let's is equal to comma A, comma I. Now, what if I want to do like this? Prints high because it goes to element 1 in the list and finds high and then prints it. Now, another mistake people make is they say, well, I want the second element of the list, so I'm going to write print lets 2. Because 2 is the second thing. I want it to print high, not just the letter A. So list index is out of range. That's because 2 should actually refer to the third element of the list, and there is no third element in that list. Okay, so that's just a warning about that. Now, I can also do things like I can combine lists just with the plus symbol. Here I'm just emphasizing this issue about the lists. So if I add, say, nums and lets, okay, I take this list, and I concatenate them, and I make a list just with all of those elements together. There are a lot of operations, a lot of neat operations you can do with lists, and a lot of them that you'll probably have to use at some point. One that's very nice is len, L-E-N. That tells you just the length of the list. So this list that I constructed here had 1, 2, 3, 4, 5, 6, 7 elements in it. So if I do len of combined, which was the list made out of nums and let, if I do len of combined, it returns 7. Okay. Maybe we should avoid going too fast. How about nums? I'll make my own nums here. Excuse me. Okay, if I do len of nums, what do you think is going to be returned by that? 5, because I have 1, 2, 3, 4, 5 things inside of that list. Okay. Okay, so that's my very brief sort of crash course on Python operations, control sequences, and lists. When you go back and start making your own diagrams, which you should definitely do if you're doing a project, a science project, then I would strongly encourage you to integrate these very nice symbolic structures inside of the structures like this. You see, I've already kind of done that. This is an if diamond right here, like what I had before. These are the blocks. Okay, sometimes you have to start writing very small. So there's some projects that you can already start to do that are kind of fun, that you can do just by manipulating lists and performing operations. So one of them is to mess around with the Fibonacci sequence in the golden ratio. Okay. In case you don't know what that is, just get situated here. Okay, it's a cool number. The golden ratio is a cool number. It gets associated with, it's got a lot of cool mathematical properties, but it gets associated with, artistic things, even mystical things, which, whether you believe in it or not, it still makes it a fun thing to play with when you're learning how to do computer programming. Well, what is it? So the golden ratio is a simple concept to explain. Say that I start with a line of some length. I've drawn a line here. It's separated into a red and blue part for the reasons that you'll understand in just a second. And what I want is to figure out how to divide the line such that the ratio of the length of the whole line to the largest subsegment is equal to the ratio of the subsegment to the smaller subsegment. So in pictures, what I mean is this. C is the whole line. So I want the ratio of C length to the length of A to be equal to the length of the A length to the length of the B length. And if I can divide a line in this way, it's called the golden ratio, expressed in equations. C is just A plus B, right? So it's just A plus B over A has to equal to A over B. And if we arrange for that, then that ratio is equal to the golden ratio. It's called phi. Okay, now let me show you a way to calculate that. And it uses what's called the Fibonacci sequence. And this is something that you can write your Python code to calculate. So first of all, I'm just going to tell you the first two elements of the sequence. It's going to be 0 and 1. 0 and 1 are the first two elements. And then after that, the dot, dot, dot means that there are going to be more elements coming. I'm going to try to use notation on this slide that evokes a computer program. I want to take the first two elements and add them together to get the third element. So 0 plus 1 is 1. So the third element is going to be 1. And I'm expressing that in a kind of equation form here. Okay. If I imagine I is going to be an index, like what you would use in a computer code. If I is equal to 1, then I would have fib of 0, which is the 0th element of this list, plus fib of 1, which is the first element of the list. And that's going to tell me what the next element is. It's going to be 1. Okay, so the full list is going to look more like this. I'm going to say 0 plus 1 is 1. Then to get the next element in the list, I say 1 plus 1 is equal to 2. Then to get the next element in the list, I'm going to say 1 plus 2 is 3. Then 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And so on and so on. I mean, you can imagine this going on forever. Now, imagine taking ratios. You can say take the ratio of each element, starting with the second, with the previous. Okay, 1 over 0 is infinity, so let's maybe ignore that one. 1 over 1 is 1. 2 over 1 is 2. Then you get 3 over 2. Okay. Then you get 5 over 3. Then you get 8 over 5, 13 over 8. And if you keep doing that forever, you eventually converge on a specific number, and it happens to be the golden ratio. So that's how you reproduce the golden ratio from the Fibonacci sequence. It's an irrational number that has a lot of interesting properties, and it turns out to be about 1.618, which you can check for yourself. This is what I mean to be symbolizing here. As I goes to infinity, as you go to higher, higher, farther and farther along down this line, you get infinitely close to the actual value of the golden ratio. Okay, so I think you can probably see what I'm suggesting here. Go ahead and open up Python, maybe a Jupyter notebook, and create a list. Step 1 is just create a list of the Fibonacci numbers. Okay, and then there are some interesting things that you can just play around with. Remember, I talked about the mod operation. Imagine applying, say, mod 3 to every element in the Fibonacci series. Try doing that. Try doing a code that does that and writes out the result. It's kind of interesting what you will see. And then do it for, say, mod 4, mod 5, etc. And once you get that going, there's some fun things that you can play around with there. The other thing is to get exercise in making graphs. Make a graph showing the numbers plotted as a function of the position along the series, and show how they, and then take the ratios, take the ratio of 1 with the previous, and show how it converges to the golden ratio. You probably don't want to start with 1 over 0, but start with the one after that. Okay. And then finally, maybe slightly more advanced, have it draw a line like this. Have your computer program draw a line like this that actually takes a line and segments it into pieces according to the golden ratio. Okay, and if you want something really, really advanced, look up how the golden ratio is related to the golden spiral, or the Fibonacci spiral, and try to generalize this into what is called the Harris spirals, which you can learn about on Google if you get bored with what I've assigned here. Okay, so we're now at 4:51, 9 minutes left. So I think this will be a place where I stop for today, unless anybody wants to discuss anything. No?
No, I think we fielded all the questions.
Okay. Okay, so I guess the next time we meet will be Thursday. Is that the idea?
It's Friday.
Friday, okay. Friday at 3 o'clock?
Yes.
Okay. Good. All right, so then if there's nothing to say or do, then maybe we'll call it a day. All right, thanks everybody for their attention, and see you on Friday.